This is Bob Ross here. I know you're talking about.
Don't waste too much marker.
You're gonna throw the mark.
Stop. Stop.
No, see, I have to finish this Bob Ross page. No, this is very important.
All right, thank you. Thank you so much. All right, gather back together. So, thank you. Do you want to return to your seat so I can assert my dominance?
Yes, but I have to label it. It's a Bob Ross page.
That's it. Go get him.
Thank you. He complies. Okay. Anyways, it might be obvious what mechanical does, but then on the other hand, right? What do we do behind those closed doors with all those loud machines? As Calvin said, they make a priority list and strategy on kickoff, and that is really important to mechanical. That priority list essentially drives our design throughout our entire process, throughout the entire season. And so the way it was laid out last year, we had 6 weeks to do all of this. So kind of our robot building process was divided into 3 phases. The first one being design and prototype, right? Before any fabrication happens, you want to make sure that you have a solid plan for how your robot's going to look. And then so we start that off with good old-fashioned whiteboard markers, just drawing up mock concepts. And this is where everyone gets out a radical design, and we all get together at the end of that to kind of converge on one design that we might want to pursue. And so after that, we head into CAD, which is computer-aided design. It's a fancy way of saying 3D modeling. And so we model the entire robot before we actually begin any fabrication. And then so on top of that, we add later on to designs and iterate, but we'll get to that later. And past that, we're maybe at, I don't know, week 2, week 3. We've started fabrication, starting first, of course, with our drivetrain, because the drivetrain is pretty much the foundation of our robot. And then once that's done, we head into the other various mechanisms on the robot. And then we kind of stagger fabrication and assembly. Once a little bit of the fabrication gets done, we can get started on a couple of the key components, such as here with the drivetrain. We've finished fabrication for the drivetrain at this point, and we're starting assembly, but we might still be fabricating, I don't know, like an elevator or other mechanism. Yes?
What about construction?
Yes. So construction is a subdivision within mechanical, and their role is very important. In fact, they make these analog mock kind of practice. Let me practice this. So on the fields, you saw those rockets, right? So having a kind of way to practice is really important. And so what construction does is on kickoff day, they first provides all these blueprints and drawings of how a rocket is laid out in a wood mock-up, essentially. And they make these wooden analogs of these rockets for us, so we have the ability to practice with them throughout the rest of the season. And yeah, so this next video here is just essentially outlining the design process. It is by Grant M. Hara. If any of you know Mythbusters, you'll know him.
Hi there, my name is Grant Imahara, and I'm one of the hosts of Discovery Channel's Mythbusters. I'm also an electrical engineer, a robot builder, and, oh yes, a former FIRST mentor. I'm here to talk to you today about the importance of design. Look, I know what the first season's like. It's intense. Everyone wants more time, right? Well, you don't get more time. No, you don't. But through design, you can make better use of the time that you have to be more efficient and get more done. Now, I know it's tempting to just grab a piece of aluminum and start building the first thing that pops in your head. I know, I have. But this really only works for very simple challenges. And as we all know, FIRST is anything but simple. FIRST robots are, by nature, complex machines. In order to build them with the capabilities that you want, given the time that you have, requires careful thinking. The design process is your roadmap through this minefield. Seeing that journey and understanding the process of design is what this video is all about. Now you're saying, I already know all this, Grant. What's the difference? Well, the difference I'm suggesting is that you pay a little more attention to the very early stages of your design process. Now you're probably thinking, whoa, 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 we do design. We draw it on a piece of paper or on a whiteboard and then we build it. Well, before charging forward to making parts, just take a little time to make a study model. It can be in the computer using CAD, computer-aided design, or it can be popsicle sticks and paper towel tubes. It doesn't matter what you use, as long as it helps you work out the problems. Because, let's face it, making a part over and over and over again is not only frustrating, but also very time-consuming. You know what I mean. Make a part, test it, take the assembly apart, put it on the drill press, drill a new hole just a little bit further, put it back together, rinse and repeat. In the end, you've got something that looks like a piece of Swiss cheese rather than a robot part. By using a model to test your ideas before making parts, you'll save materials and time. What? You don't believe me? It's already been done by many teams. I'll show you. Within FIRST, there are hundreds of instances of great design, but today we're going to focus on one notable example of excellent robot design. Team 111, Wildstang, and their lifting arm. This is their design story. Step 1, define. Understanding the problem. The challenge was to pick up an inner tube from the floor and lift it up 8 feet, using a mechanism that was limited to an initial height of only 5 feet. Their design needed to be strong, lightweight, and controllable. These requirements and constraints defined the problem that they had to solve. The team started with a review of the required geometry, called the kinematic analysis. Basically, how small did the robot have to be to begin with, how long the arm had to extend, and the types of movements required. They used hand sketches to quickly identify the critical dimensions. Based on this analysis, they established that 2 linkages connected by rotational joints could accomplish this task. Step 2, ideate. Brainstorm. As a result of their discussions and brainstorming sessions, the team decided to model their robot arm on a human arm. The robot arm would rotate along 2 axes at its shoulder and along a single axis at its elbow. They decided to make each aspect of the arm analogous to a human's, with linkages as bones and power sources as muscles. Next, they had to build what they imagined. Step 3, create. Building. Team Wildstang used the CAD approach, building their arm in the virtual sense, in the computer. But as I mentioned, you can use whatever you want to make your models. They divided the arm into its major components, the shoulder, the upper arm, and the forearm/gripping system, and assigned each part to a different sub-team. These sub-teams worked independently to model their designs using CAD, and then put all the models together for testing. Early testing revealed that the original gripping system could hold a tube, which is good, but the tube rotated if you moved the arm too quickly, which is bad. Within the computer, they then easily moved around the pivot points until the arm had better range of motion and a stronger grip. The whole time they kept plugging away at the models to improve performance. See, they did all their testing in CAD and solved the problem virtually before any of the parts were actually made. Their computer corrections solved real-world problems. Now that their virtual design was working great in the computer, it was time to make the parts, put the robot together. Step 4, solve. Manufacturing. Wildstang's CAD models not only helped them test the arm, but also served as detailed blueprints for fabricating the actual arm components.
So yeah, you get the idea. That's just an example of the design process for one other team. And so next I'll kind of go into kind of how our season looked. And so here is CAD, and this is what you might see us sending back and forth to each other in Slack, which is our communication platform. And so we're just kind of like drawing on each other's parts, adding on to it, giving suggestions, and we'll just send these to each other and kind of iterate on each other's design before we kind of arrive at a final design. And so that is CAD, and eventually we will end up with something like that. Okay, whatever. I'll just explain what happened in that video. After we finish all the CAD, well, as I said, we kind of stagger the process a little bit. So some of the CAD can get done, and then we'll start fabrication. The thing that was in that video was an example of our CNC actually cutting out a part of sheet metal to fabricate this component, which I believe was our suction arm, which didn't end up getting onto the robot. That happens all the time, don't worry. And so this is just an example of some of the stuff that you can make on our CNC router. You get these beautiful sheets with beautiful pockets in them. And so all these pockets, all these details within the sheet metal is actually something that you CAD in. So the designer will have to make these pockets manually. It really becomes an art form at this point. And so the CNC can cut many things, not only sheet metal. So that's an example of rectangular tubing or box tube. If you saw our robot Friday, those towers that you saw on our elevator, that was made of box tube, and as well as our drive rails and pretty much all of the superstructure. So that's an example of box tube and all of that. That is something that we can make on the CNC router. And if you choose to join mechanical, we'll train you on that immediately. And then we progress into assembly. So this is an example of the first thing that we assemble, which is our drivetrain. We start out with that because, once again, it's the foundation of a robot. You can't really build on top of that without it. So our assembly space is kind of a mess. It eventually gets like that because entropy. We would like to kind of reform this process a little bit, give a bit more organization to it. But yeah, that's something we're working on. But you might find our assembly space to look something like this.
Should I just sign it?
Yeah, sure.
Oh, I have to go and do this. Oh my gosh.
Oop, that one.
Want to see the CNC video or no?
Sure, we'll go through it. Oh. Yeah.
Yay. It's very loud.
It's very loud. So yeah, this is a tool in our workshop that literally excavates parts using something that looks like a drill bit, but it's actually a bit different. It's called an end mill. And so this mill is going around and excavating aluminum out of the sheet. And so it's actually chipping away part of the aluminum. And you can see all those chips flying out of it. And eventually you end up with something that resembles the profile that you CAD'd out. Thank you, Amelia.
You're welcome.
And then after we do the assembly, it is testing time. So we don't assemble all of the robot. At this stage, it's incomplete, but you can loop it, I guess. Right click and move. Thank you. At this point, our robot's not completely done, but we can use batteries and plug them straight into our motors to test a couple of our components, such as our elevator. And then it's more testing time. Eventually, we'll add on more and more until there's we have the capability to test more. And so yeah, that was one of the challenges, as Calvin mentioned, which was during endgame we had to get up on these kind of platforms, and essentially the challenge was getting upstairs, right? And so this was the way that we approached it. Other teams obviously had many different and maybe superior ways of approaching it.
He graduated, don't worry about it. Oh wait.
And then at this point, we are not done. So actually, in our previous season, we actually attended our first competition at SCR, and then we made this iteration. So yes, things will happen in between competitions while, build season's done already, but you're still adding on. So this is actually our hatch mechanism, the mechanism that handled or manipulated the hatch panels that you saw. And so this first iteration we lovingly dubbed the Demogorgon because it kind of played out like a Demogorgon from Stranger Things. But then we decided that we could improve on this. And then we opted for a design that we saw somewhere else. That happens very often. From a team 987, High Rollers from Las Vegas. And so their design was kind of this one-prong finger, essentially. Like, we had this idea at the beginning of build season, at kickoff, but we decided, like, I don't know, it might be too inconsistent. But once we actually see this working out at competition, we decided, you know what, we'll give this a try. And so that'll happen a lot as well. And another interesting note, it's not just a finger. This kind of back pusher plate is attached to the entire finger mechanism, so it will retract back along with the actual finger. And that kind of pushing action helps us push out the hatch, which our previous iteration did not have. And there's an example of it on our final robot. It's kind of blocked by someone's hand, but you get the idea. I think that's it, though.
Yeah.
All right, awesome. Thank you, guys.
Not. You're good to draw a second Bob Ross, maybe.
Try not to waste as much ink though.
No, don't.
You have 25 seconds.
Does anyone have any questions, by the way, for Justin?
The 10 seconds are over.
Okay.
Hello. So, don't worry, the anatomy and biology gets a lot more steps. So I'm the head of controls, Adam. And so while mechanical might be responsible for creating the bones of the body, so to speak, controls is like basically responsible for everything else. So in terms of, sorry, what?
It's an analogy.
Yeah, oh yeah, it's an analogy. Not actually,
We're
okay.
comparing a body to a robot.